So hello everyone, welcome to BrainMap. This seminar series is co-sponsored by the P41 funded Center for Mesoscale Mapping housed in the Martinos Center. It's my great pleasure to introduce our speaker today, Geoff Parker. Dr. Parker is a professor of healthcare engineering and imaging at the Center for Medical Image Computing at UCL. His research focuses on the development of quantitative MRI methods and their application in a range of organs and pathologies. He has made contributions to fields including diffusion MRI, dynamic contrast enhanced MRI, and oxygen enhanced MRI. He's an ISMRM fellow and a member of the ISMRM Board of Trustees. He's also active in technology translation to healthcare application and currently CEO of Bioxident and a director of Queen Square Analytics. I would just like to remind the audience to please address any questions using the Q&A box and raise their hands. Dr. Parker, thank you very much for coming today. The virtual stage is yours.
Thank you very much for that introduction, and thanks very much for inviting me to speak. It's a really exciting opportunity. So yeah, I'm Geoff Parker. As was just described, in addition to my UCL role, I am also involved in tech transfer and am involved in a couple of companies, Bioxident and Queen Square Analytics. And I just declare that just by way of transparency, although there's little in what I'm going to talk today that is directly relevant to either of those companies. So I'm going to talk about blood-brain barrier measurements using MRI, and hopefully the slightly cryptic new methods and old will become apparent as I go through my presentation. I'm going to talk about three different methods, and so the talk naturally splits into three separate sections. So I'll pause after each section in case anyone has any questions. Otherwise, we can leave them until the end. Let's see. Okay, yeah, so the blood-brain barrier. I'm assuming most of you are aware of the blood-brain barrier and roughly what it does, but just in case, here's a sort of entry-level description. The blood-brain barrier essentially separates the blood in the vasculature of the brain from the brain tissue, and it's there fundamentally to restrict and regulate molecular passage from the blood and into the tissue, and also to regulate the clearance of waste products in the other direction. So it's a very important protective organ within the central nervous system, and you know, without it, the potential for toxins to get into the brain would be much higher. The blood-brain barrier allows certain substances through but restricts others. This diagram here gives an idea of how that can happen. There are a number of specific channels in the blood-brain barrier which actively transport specific molecules. So hopefully you can see my cursor. Someone shout if you can't. But for example, here we have in blue aquaporins. This AQ stands for aquaporin. And aquaporins are a class of transporter that actively move water from one space to another. And here we've got aquaporins in the blood-brain barrier, which are transporting water through the blood-brain barrier. They're also present on the astrocyte end feet. We have aquaporin transporters here as well. So water can get from the blood into the brain through that actively transported mechanism via the aquaporins. In disrupted blood-brain barrier, when the blood-brain barrier is damaged due to some form of pathology, these things here, this black line represents what's known as a tight junction, and the tight junctions are the joins between the cells that make up the blood-brain barrier. So the blood-brain barrier surrounds the capillaries in the brain. It has these endothelial cells, which is what EC stands for. And these are very tightly packed up against each other with no gap in between, and that tight packing, the point at which they join is the tight junction. And again, in disease, that tight junction can be damaged, and if that tight junction comes apart, then there's the potential for transport of molecules of all sizes through the blood-brain barrier from the blood into the brain. So in summary, the blood-brain barrier is an important organ there to keep the brain healthy and to regulate transport of various molecules. So the blood-brain barrier does get damaged in disease, and its disruption is associated with quite a few well-known pathologies. So in a situation where you have angiogenesis, such as in cancer, the disordered growth of vasculature within a tumour tends to occur without a blood-brain barrier or disrupts the existing blood-brain barrier. The presence of inflammation, so for example in multiple sclerosis, which is the example shown on the right, can also lead to a breakdown in the blood-brain barrier, and essentially anything that's wrong with the blood vessels themselves, so angiopathy, such as may be found, for example, in Alzheimer's, can also lead to dysfunction of the blood-brain barrier. So it's very widespread, implicated in a number of different conditions, and therefore being able to monitor the breakdown in the blood-brain barrier is potentially useful for quite a wide range of diseases. And there are broadly two approaches for assessing blood-brain barrier function. The sort of classic method is using contrast agents, so gadolinium-based contrast agents, and the sort of quantitative method for evaluating the rate of transfer of contrast agents across a damaged blood-brain barrier is dynamic contrast enhanced MRI, or DCMRI. And the second approach is or the second established approach anyway, is to measure the passage of water across the blood-brain barrier. So in other words, water exchange across the blood-brain barrier. And we've already seen on the previous diagram that water is actively transported by these aquaporins. And when we see the breakdown of the blood-brain barrier in those tight junctions opening, we would expect both contrast agents and water to flow more freely across the blood-brain barrier. So the default approach, radiologically speaking, has been to look at gadolinium contrast agents and how they leak. Radiologically, that's usually a qualitative assessment. Is there leakage? But DCMRI gives us the potential to become a bit more quantitative in how we assess that leakage. Okay, so the gadolinium-based contrast agent methods are nice because they're relatively straightforward, really well established. You can perform a DCMRI measurement very easily using a T1 weighted spoil gradient echo style acquisition. And the analysis methods for DCMRI are well known. I'll give some examples in a minute. The downsides, though, to using contrast agents to assess the blood-brain barrier is that the chelates that carry the gadolinium ions are relatively large. So a typical chelate that surrounds the gadolinium ion and limits its toxicity, typically around 500 Daltons. And so they're relatively large and they don't easily leak across the blood-brain barrier, particularly when those tight junctions are intact. And so this means that DCMRI has some drawbacks when used to measure blood-brain barrier breakdown, a relatively low contrast to noise ratio in the measurements that are feasible, except in the situation where you have really severe breakdown, such as in that example I showed earlier where there was a brain tumor. So this movie gives a sort of idea of gadolinium-based contrast agent delivery and leakage in practice. So you will have noticed this isn't a brain, this is a hand, and we're focusing here on an individual with rheumatoid arthritis who's got a lot of inflammation in their wrist. And so the area that's highlighted there is the bones of the wrist. And you can see in amongst the bones of the wrist, as we go through this time series, contrast agent arrives and the tissue enhances very rapidly. And the reason it doesn't only enhance rapidly, it stays enhanced as well. And that's because the blood vessels are extremely leaky in the presence of inflammation within the wrist of this individual with rheumatoid arthritis. So this is a really clear example of gadolinium leakage. However, when we look at the brain, the situation isn't quite as clear. So this is an example of a DCMRI acquisition in the brain of an individual, I think, with cerebral vascular disease. And a few things are apparent. First of all, the individual is moving, as is often the case with patients. Secondly, there's quite a lot of artifact in the image. You can see quite a lot of ringing around the edge of the image due to the presence of the scalp. The image is quite low signal to noise due to the fact that it's a dynamic acquisition. And as the movie loops, you can see the contrast agent arriving, the vessels become bright. And the loop will start again in a minute and you'll be able to see that. But what you don't see is much evidence of the parenchyma becoming brighter due to the presence of the contrast agent. And that's because the leakage is really quite subtle when you've got largely intact blood-brain barrier present. And the leakage, the magnitude of that leakage is of the order of the sort of artifacts that you can see in the image. So the noise, the Gibbs ringing, the motion all serve to make it quite a difficult measurement to extract the rate of uptake of your contrast agent using DCMRI in the brain. Nevertheless, we have been doing that. And so the approach that we've used is a very sort of standard DCMRI approach, dynamic contrast enhanced MRI approach, using a model known as the TOFS model, or the Ketty model, extended to include a blood volume. And what we're trying to establish here is the rate of transfer of the contrast agent from the capillaries of the brain, which in this diagram are represented by the red dashed lines, and the little green circles are the contrast agent molecules that are leaking into the brain parenchyma from the vasculature. And if we've got leaky blood-brain barrier, we'll get a high value of K-trans. There'll be a lot of leakage of the contrast agent. And we can use this simple setup to construct a compartmental model. And the classic model, this TOFS model, extended TOFS model, can be expressed like this. So the concentration that we measure in the tissue, in the parenchyma of the brain, is made up of a concentration in the blood pool plus this term over here, which accounts for leakage of the contrast agent from the blood into the extravascular space. And the parameter that people are usually interested in is this thing called K-trans, which quantifies the rate of leakage of the contrast agent from the blood into the extravascular space, and also potentially blood volume. And so this is a technique that works, and one that we've spent some time on at our centre. And this is an example carried out in collaboration with some colleagues of mine at the University of Manchester, where I used to be based, using that dynamic contrast enhanced MRI technique to understand or perhaps shed light on what might be going on in idiopathic Parkinson's disease. So it's previously been noted that blood-brain barrier breakdown does exist in at least preclinical studies of Parkinson's disease. But there's little data on this clinically. So we set out to use DCMRI to see whether we could improve on that situation. And so in this particular study, we had 49 Parkinson's patients, which was split into three groups. There were the Parkinson's patients themselves. There was a control group who had cerebrovascular disease but weren't Parkinson's, and then there was another control group which was healthy controls. And I'm just going to show the results of the healthy controls versus the Parkinson's patients. And so the point of what we're showing here, what I'm showing here on this slide is the results from that study, where we have taken each of the individuals and generated a group map of the parameters of interest. So we're now mapping that K-trans parameter, for example, if we look at this map on the left, across the control group, however many that was, 31 controls, to give a group level representation of the level of leakage that you would expect across the blood-brain barrier in a healthy individual. And so you can see that the levels of leakage are relatively low on the scale of things when it comes to K-trans. This is a relatively low value. If we were looking at a tumour, for example, the values would probably be at least a factor of 10 higher. But we are able to detect, at least at the group level, in the healthy control group, finite leakage across the blood-brain barrier of our contrast agent. Similarly, we're able to generate maps of blood volume from our control group. And if we compare that with the Parkinson's group, you can see that there is evidence of elevated leakage of the blood-brain barrier. So particularly in the sort of occipital areas, we're seeing relatively high levels of K-trans, indicating that the capillaries that are present in these regions within the Parkinson's group are leakier than in the control group. So confirming this idea that blood-brain barrier breakdown is present in Parkinson's disease. Interestingly, if we look at the blood volume map, it looks very similar to the controls, and we weren't able to establish any significant differences in blood volume between the Parkinson's group and the control group, even though we were able to detect these differences in blood-brain barrier permeability. So that's great. We can use contrast agent in certain settings to help us understand what's going on in various neurological conditions in terms of blood-brain barrier breakdown. But as I've mentioned before, it is relatively low contrast to noise as a measurement and therefore insensitive. And so these graphs on the right here are from a paper by Armitage et al., so not from our group, back in 2011, but it gives a really nice indication of the challenges that we experience when we try to do DCMRI in neurological conditions. The graphs on the right are showing at the top the degree of signal enhancement, at the bottom conversion from signal enhancement into contrast agent concentration. If we look at graph C, you can see the concentration in these top two curves is the concentration of the contrast agent in the blood. And then these curves that you really can't see at the bottom of the graph are representing the change in concentration of contrast agent in the parenchyma due to the leakage of the contrast agent. Part D in this graph is the same data on a different scale, so that we can see what's going on within the parenchyma, and you can see that we are able to measure some leakage, so that's great, but it's noisy. And if you look at the labels up here, which are splitting this particular stroke group into two subgroups, you can see that they largely overlap. It's very difficult to distinguish the two subgroups, and really the take-home message is that DCMRI is noisy and insensitive, and the fundamental reason for that is that you've got these big molecules that struggle to cross the blood-brain barrier. Okay, so before moving on, that's kind of the first bit of my talk, just summarising, if you like, what's possible with DCMRI, which is the sort of, let's call it the old-fashioned way of measuring blood-brain barrier breakdown. Do we have any questions before I move on? I think there's one in the chat.
Yeah, there's just one in the chat, Daniel. So I can ask actually right now so that we move a bit faster. In the PD examples, have you been able to look longitudinally and over what period?
No, this is all.
Question.
So the first question is no. This is cross-sectional, so we don't have the longitudinal data, unfortunately.
Okay, so second question. Have you been able to correlate any challenges in blood-brain barrier with disease clinical presentation or other brain MRI measures?
Yeah, we do have other disease scores. I can't remember what the relationships were, but I can share those with you offline if that's of interest. Drop me an email, and yeah, I'll be happy to share with you what we know about that.
Okay, thank you very much.
Okay.
One more question. Is there optimal temporal resolution for subtle BBB leakage?
Yeah, that's a really good question, and there's a short answer and a long answer. The long answer is that, well, I won't go into the long answer, but it really depends on exactly what you're trying to measure. For example, if you're trying to extract blood flow measurements at the same time as measuring leakage, then you need a much higher temporal resolution. Whereas if you're content just to limit yourself to things like blood volume rather than blood flow, then you can afford to go to a much longer temporal resolution. And the main consideration is signal to noise ultimately, and the spatial resolution that you want to obtain. The short answer, I'll stop the long answer there. The short answer is that I recently co-authored a paper that went into a lot of these considerations in some detail. And again, I'll be happy to share that paper afterwards if you want to drop me an email.
Okay, thank you very much.
All right. Okay. Right. I think there's maybe a question in the chat as well.
There will be questions
Okay. All right.
at the end.
Okay, I'll carry on.
Okay, thank you.
Right, so an alternative is water exchange, and I apologise for this gratuitous use of a video or an animation that a colleague of mine put together for a bit of public engagement work that we were doing. But the point here is that we're not limited to looking at gadolinium to measure blood-brain barrier breakdown. We can use water as an alternative tracer. And so we're going to look at the diffusion of water across the blood-brain barrier as an indicator itself of blood-brain barrier dysfunction. And so this is ultimately a measure of water exchange between two compartments, between the blood compartment and the extravascular compartment. So water exchange, or WEX, as I'm going to abbreviate it occasionally. So there are various methods that have been proposed to measure the rate of water exchange across the blood-brain barrier. So, for example, a number of groups have looked at arterial spin labeling as a way to probe this. After doing the labeling of the inflowing water and allowing the blood to arrive within the tissue of interest, clearly the water is going to permeate away from the blood into the extravascular space, and there's been work into characterizing the degree of leakage using those arterial spin labeling methods. Turns out you can't use arterial spin labeling on its own. You need to introduce additional sensitization to give you enough contrast to noise, and one approach to that is to use diffusion sensitization. Others have used relaxation time sensitization. So in this case, it was looking at T2 combined with arterial spin labeling, taking advantage of the fact that you have different T2s in different compartments. Contrast enhanced arterial spin labeling is a technique that we've investigated and had a nice RIM abstract on last year. A technique that's come to relative prominence recently is called Webcast, which is from Hangjiang Liu's group, which doesn't map blood-brain barrier permeability at a voxel level, but gives a whole brain estimate of blood-brain barrier disruption. There have also been approaches using relaxometry techniques. So this is a technique that we published a couple of years ago, 3 years ago now, using exploiting T1 differences between compartments, particularly in the presence of contrast agent, to measure water exchange across the blood-brain barrier, and also techniques that just use diffusion MRI-based approaches to measure water exchange. And these approaches, this last class of approaches, are based on the filtered exchange imaging technique, or FEXI technique. And there was a paper that was published just a couple of years ago outlining how this can be done. And I'm going to spend some time talking about this FEXI technique and the work that we've been doing on it. So the FEXI approach is basically a double diffusion encoding diffusion MRI method. It's been used previously mostly to look at water exchange across cell membranes, and that's what it was originally designed for. And it's only recently that it's been adapted for looking at blood-brain barrier water exchange. The current implementation, apologies for the wordy slides, by the way, but the current implementations of FEXI generally estimate something known as the apparent exchange rate as a proxy for sort of, if you like, true rate of water exchange. And so this goes by the acronym AXR, apparent exchange rate. And it turns out that, as is shown in a paper that I'll reference in a moment, AXR is only an approximation of water exchange. It is actually in practice a composite parameter that includes contributions from the relaxation times in different departments, compartments, the volume fractions of different compartments, so the volume fraction of the blood pool, for example, in this case, and also the diffusivities of those compartments. So the work that we've been pursuing recently is designed to answer the question, is it possible to be more specific with water exchange measurements when using this FEXI approach and avoid some of those confounds? So the FEXI measurement looks something like this. So for those of you who've done double diffusion encoding MRI, this will look very familiar. For those of you who've not done any diffusion MRI at all, it might look a bit baffling. But effectively what's going on here is that we have two blocks. The first block is known as the filter block. This is designed to deliver some diffusion encoding to the system that we're looking at, in this case the blood and the extravascular water, and to preferentially suppress one of those compartments relative to the other. We then wait for a period of time, which is denoted by this TM, which stands for mixing time. And during that mixing time, the water that's in those two compartments has an opportunity to permeate across the blood-brain barrier. So the longer we wait, the more permeation of the blood-brain barrier can happen. And then we have a second diffusion measurement here, which is known as the encoding block. And we use this to probe the diffusion MRI signal that's present after that mixing of the compartments has occurred. And so if the blood-brain barrier is disrupted, we would expect that mixing to happen more rapidly than in the presence of an intact blood-brain barrier. So this was originally introduced by Marcus Nielsen's group almost a decade ago now. And this diagram gives a sort of schematic representation of what I was just describing. So this diagram has time along the horizontal axis and effectively signal, or in fact, the ratio of something called ADC primed over ADC, but think of it as signal for the time being. Before applying the filter block, you have your water in your two compartments. We call that blood and extravascular signal for our purposes. We apply the filter block, and that's going to preferentially knock out the signal from one of the compartments. And for our purposes, this is knocking out the signal from the blood pool, whilst leaving the signal in the extravascular space relatively untouched. As I was just describing, if we then wait this time, TM, mixing time, we start getting exchange, mixing of the water between the two compartments. And we can monitor how the signal recovers over time by measuring the ADC, and this ADC prime, the effective ADC, as a function of time. And that tells us something about the degree at which this intermingling has happened, and that's parameterized by this AXR, apparent exchange rate. So that's great, and excuse me, and it works. So this is from the paper by et al, demonstrating that it's possible to map this apparent exchange rate on a voxel-wise level across the brain. So it's quite smooth, but nevertheless we are getting voxel level AXR estimates. And so what we're doing here is we're using our filter block to suppress the blood pool. Think of an IVIM experiment. If any of you have done IVIM, we're knocking out the blood pool at the low B values, and then we're allowing the mixing to happen between the blood pool and the extravascular space, and that's telling us about the degree of blood-brain barrier breakdown. Okay, so as I mentioned, though, this AXR parameter is subject to bias. There's a paper that came out last year which looks at some of these different aspects of bias, as illustrated in this example on the right. They weren't looking at the blood-brain barrier, they were looking at cellular exchange, but the principles are the same. And in this case, you can see that as you change this parameter Fi, which is the fraction of your intracellular, or the intracellular fraction within your tissue, so in other words, how densely packed cells are, AXR estimates can vary quite substantially, with quite significant bias relative to the true exchange rate, which is shown in this red line at the bottom. So particularly at extremes where you have high or low volume fractions, you can get very severe errors in your apparent exchange rate, or at least contamination of the apparent exchange rate, which makes it much more difficult to interpret. So can we improve on that situation? But the approach that we've chosen to use is to go back to compartmental modeling, so the sorts of techniques that we were using for the gadolinium based measurements of blood-brain barrier, but applying those instead to what's going on with the diffusion-based exchange measurements that we're looking at here. So we can set up our compartmental system. So here we have an intravascular space at the bottom, which is our denoted VB for blood, and an extravascular space up here, which is VE. And they have their own water populations as characterized by these parameters P. And there's a rate of exchange that can be defined in both directions between these two compartments. So the rate of exchange from the blood into the extravascular space, which we'll call K in, and the exchange in the opposite direction. Another parameter that is sometimes used, which is sometimes intuitively helpful, is the residence time. So how long a water molecule will typically stay, for example, in the blood pool before permeating out into the extravascular space, and that's simply the inverse of the exchange rate. So the residence time in the blood is the inverse of this exchange rate, the rate of going from blood to tissue. And if we choose to, we can, and if we've got a measurement of blood volume, VB, we can use this information to tell us specifically about the permeability surface area product of the blood-brain barrier to water. So I apologise for the fact this slide is a bit sketchy. I lost some slides this afternoon, so I had to rapidly recreate it just before this talk. But what we're doing here is we're setting up our compartmental model in terms of the signal contributions from two fractions, which are shown in this top equation here. We have our blood fraction FB, and we have our extravascular fraction FE, and we assume that those two compartments sum to 1. We have diffusivity in the blood, dB. We have a diffusivity in the extravascular space, dE, and we can. These fractions here are a function of the mixing time within our FEXI experiment. So as mixing time progresses, we expect more of the unsuppressed spins from the extravascular space to move into the vascular space. So this fraction of spins that are present in the vascular space that are visible will increase as a function of mixing time, and that enables us that's how we get at this exchange rate K, which is shown here. So this is our estimate of K that we're aiming to extract using this compartmental model rather than using the AXR, which is the default method used within the FEXI implementations that have been there to date. So the attractions of doing this are, because we're explicitly accounting for the diffusivities of the blood and the extravascular space, because we're explicitly accounting for the volume fractions of the blood and the extravascular space, they can all be either compensated for or extracted from the fitting process at the same time, yielding a more meaningful, hopefully, estimate of the rate of exchange K. Okay, so at the same time, we've looked at the impact of relaxation times, relaxation effects, and again, apologies for the poor quality of the slide. So we know that blood and tissue have different T1 and T2, and these graphs on the right are the arrows are designed to indicate the sort of typical difference that you'd see in T1 between blood and tissue here, and in this case, the difference that you would expect to see in T2 between blood and tissue. And it turns out that this leads to substantial biases in your ability to estimate your transfer coefficient K. If you don't account for it, then there are substantial errors that creep into your AXR measurement. So, for example, if we look down here at the T2 graph, if you don't account for T2, then your apparent exchange rate could be out by somewhere between sort of 20 and 40%, which is obviously a big error. Happily, though, when we use our compartmental model instead, the errors are much reduced, as shown here in the solid lines, but they're still not negligible. So we're still getting sort of 10% errors potentially due to T2 in particular, even when we're doing the compartmental modeling. So we've accounted for that. This may be a slide that I lost. Yeah, I think it is. It's a slide. Oh, here we go. I skipped the slide. We have accounted for that those relaxation time effects here by introducing via this matrix formulation the impact of both T1 and T2 on the magnetization that we're ultimately measuring to give us our diffusion signals. So again, with a two compartmental model, we're able to include the T1s and T2s of both the intravascular and the extravascular space in our overall formulation when it comes to working out the exchange rate between the two compartments. Okay, so that's the theory, and those are the simulations. We've now applied those to a healthy volunteer group. And so what we've got here is, if we just focus on the two right-hand columns, two different acquisitions that were required to enable us to generate AXR data. So that's the traditional FEXI approach, and also to enable us to use this compartmental modeling. As you can see, the compartmental modeling requires some additional B values relative to what we can get with what we need for FEXI, which are actually encoded at the bottom here. And you can see the mixing times that we've used throughout the experiment as well. So this is a relatively small data set, just 6 healthy volunteers who we scanned twice on a 3T system. And so what we saw looked something like this. So this is our apparent exchange rate. Which is shown here down here at the bottom. So we're able to replicate what Bai et al. Were able to show in terms of voxel-wise measurements of AXR across the healthy brain. The top is the ADC measured using this technique, and this middle parameter sigma is the labeling efficiency, effectively, of the filter block. In the middle here, these are the results of applying our compartmental model. So at the bottom we have this parameter K. As you can see, the fit's a bit more unstable than the AXR fit, but that's what we would expect because there are more parameters being fitted. In the middle, we have the diffusivity of blood, and at the top, we have the diffusivity of the extravascular space, which are also generated through this model. And then on the right, we have the same model, but now with the relaxation time effects included as well. And you can see there are subtle differences in this K parameter that are due to the incorporation of the relaxation effects. And if we then plot those across the group, so it's a really busy slide. At the top, we've got our AXR measurements. We've got the 2 scans for each of the individual scan, rescan. And I think the first thing to take away from this is that the measurements are, quite nicely repeatable across white matter and grey matter. So this is the ADC, this is that labeling efficiency, and this is our AXR parameter. But if you focus on the graph at the bottom, down here in the bottom right, this is our exchange rate measured with the incorporation of relaxation effects. And not only is the repeatability quite good, but also we observe that the exchange rate seems to be very similar between white matter and grey matter, which is, I guess, what we would expect, which wasn't the case when we weren't accounting for relaxation effects. So relaxation effects do seem to have a material impact on this modelling. Okay, so that's the end of what I have to say about water exchange. Does anyone have anything that they'd like to ask me about that before I move on to the last section of my talk? If not, one question, 2 questions.
Sorry, I forgot to unmute myself. So the question is there a solution to identify water exchange based on direction to quantify exchange from intravascular to extravascular ratio versus exchange from extravascular to intravascular? Or can you compare these two?
Well, from a mass balance perspective, we expect them to be equal. The same overall number of water molecules should exchange in both directions. At least at a coarse estimate. There may be water exchange. Well, there is water exchange, in other parts of the central nervous system, for example, with the CSF, and potentially into the perivascular spaces as well. But to first approximation, I think you would expect the exchange in both directions to be the same in terms of the total quantity of water that the exchange is between the two. Dan from Biogen, scan, rescan. I'd have to go back to the paper. I think it was the same day. But again, I can check that for you.
What's the difference between the 2 plots at the bottom of the right-hand side? Both are labeled K.
Yeah, sorry, I skipped over that. So this column on the right-hand side is just looking at the relationship between the different estimates of exchange. So at the top we have on the horizontal axis the AXR, so the traditional method, versus the exchange rate that we measure with the compartmental system. And you can see that there is a really poor relationship between the two. And I think this is reflecting some of those biases that are present in AXR and it actually gets even worse when you incorporate the relaxation effects. The one at the bottom is just looking at the relationship between this exchange rate if you don't account for relaxation versus if you do account for relaxation. And you can see it does have a subtle effect, but there is a difference there.
Okay, thank you very much.
Okay. All right, so for the last section of my talk, hopefully I've still got a bit of time. What else can we do? So we're not limited to gadolinium and water. There are other molecules that we can monitor using MRI. And one that's of potential interest is glucose. Certainly if you do any FDG PET, then you might be interested in knowing about glucose transport. And so obviously glucose is involved in metabolism, and we need to know how the glucose gets to the point of metabolism. Part of that is the blood flow to the brain, but part of it is also the transport of the glucose from the vasculature into the parenchyma, and that's via a couple of transporters, GLUT1 and GLUT2, which transport the glucose. So this is active transport rather than passive transport, at least in the healthy brain. So can we use these this is a measurement of blood-brain barrier function as opposed to its usual use, which is a measure of metabolism. So this is what we endeavoured to evaluate. And so again, compartmental model is the approach that we took. So we set up a model as described here. Again, we have our capillary. So we've got our blood supply here, which is now represented by CA, stands for arterial. We've got exchange rates K1 and K2 between the blood pool and the tissue, and the tissue concentration is denoted by this concentration C1. And then we have metabolism of the glucose, which is represented by this parameter K3. So unlike when we're looking at gadolinium and to a large extent water, the kinetics of glucose are governed by this thing known as Michaelis-Menten kinetics. And what that effectively means is that because you've got active transport of glucose from the blood-brain barrier in both directions, you have to take into account the fact that those transporters can be saturated. So we tested two models. The first one was the sort of classic situation where you just have these saturable transport. So K1 and K2 are described by these functions here. So Tmax and KT are the things that make this a saturable or saturatable transport mechanism, which means that basically you can only get to a certain level of transport before it maxes out. And then you've got K3 over here, which is telling you about the glucose metabolism. So that assumes that all of the transfer of the glucose via the blood-brain barrier is through these transporters. But of course, the blood-brain barrier is sometimes disrupted, and if those tight junctions that I mentioned right at the beginning are opened, then the glucose can leak out through other mechanisms. It doesn't have to be actively transported. It can diffuse out of the blood pool as well. And so this second model that we evaluated has an additional term on here, which we call KD, which is the passive diffusion of glucose in and out of the brain from the blood pool. And so this is what we're thinking might be a potential additional interesting marker of blood-brain barrier function. So again, slightly rudimentary slide, but this is what the differential equation associated with that compartmental model looked like. We can measure the rate of change in concentration in our tissue, C1, with knowledge of these exchange rates K1 and K2 and the concentrations in the various compartments. And we assume that the overall tissue concentration is made up of these two compartments, the blood pool and the extravascular space. Now, I'm not going into any detail at all about the MRI measurement here, but suffice to say we're using glucose Cecil, so chemical exchange spin lock, which gives us a measure of T1 rho, which is sensitive to macromolecular content. And we believe it's a good assumption in the measurements that we're doing here that the change in T1 rho is driven predominantly by the change in glucose concentration within the tissue. So we measure this parameter here, delta R1 rho, the inverse of delta T1 rho, using relaxivity information from the literature, and that gives us our change in concentration that we observe within the tissue. And then using these equations, we can work out the parameters of interest, the rates, and so on. And if we do that, we haven't done this in humans yet, but this is in a mouse, a mouse, I think mouse, maybe it's rat, I'm not sure now, glioma model. And if we just look at the first model, the traditional sort of saturable model, then we end up with 4 parameters. This parameter Tmax and Kt, which govern the transport via the transporters, the rate of metabolism, MR GLU, and also a measure of blood volume. And this elevated area here is where we see the tumour, although we don't see any elevation in metabolism within the tumour. And if we compare that with what we see when we bring this additional term KD into the model, we can see something that looks quite different. So rather than the contrast all being in these rate constants associated with the active transport of glucose, we see elevated passive diffusion of glucose within the area of the tumour, with the active transport rates remaining unchanged between tumour and normal tissue. And still we don't see any real evidence of elevated glucose metabolism in this particular experiment. So I'll leave it at that, just a sort of taster of what we might be able to do with glucose as an additional marker of blood-brain barrier. So in summary, I think I'm roughly on time, which is good. Hopefully I've made the case that the blood-brain barrier is an important organ to study because it is involved in so many neurological conditions. I've demonstrated that we can measure it using 3 different approaches, so gadolinium-based methods, water exchange methods, and also potentially at the end glucose-based measurements as well. And so, you know, one of the things that I'm really interested in is bringing all of these methods together to give a more comprehensive assessment of blood-brain barrier function. And so, you know, my group's going to be working on that over the next years. So thank you very much. I should finish with all important acknowledgements, because I didn't do the vast majority of this work. People that I work with did. So Lizzie Powell at UCL was largely responsible for the water exchange work. My colleagues in Manchester were largely responsible for the DCMRI example that I showed and the glucose example that I showed at the end. So thank you very much.
Thank you for this great talk. I once again want to remind the audience that they can just type their questions on Q&A or raise their hands. And Bruce already had some questions, so Bruce, could you please unmute?
Hey there, that was a fantastic talk. Enjoyed it very, very much. Very comprehensive view. I've got a question on kind of the first 2 elements of your talk. First, with regard to the contrast agent approaches, a lot of that, insensitivity is related to, the noise of the measurements. What do you think is the dominant source of the noise? Is it motion related? As you say, it's hard to hold still for the longer period of these studies. Is there something else contributing to it? From a pure SNR standpoint, one might imagine those techniques could be much more sensitive than things, for example, looking for small water contributions. Yet in practice, that's not the case. So what's dominating the noise?
Yeah, I think it's multifactorial, but probably the biggest single thing that I get concerned about, at least, is the point spread function from the vasculature. So you have such a high concentration in the blood pool, and clearly you've got major blood vessels close to many of the tissues that you want to evaluate. You know, the cortical grey matter, the hippocampus, whatever it is that you're interested in, and you can just see it on that dynamic example that I showed earlier. You know, a point spread function from a vessel, when you have such a very high concentration in the vessel, is going to cause contamination distant to that vessel. And the amplitude of that contamination is of the order of the signal change that you would expect to see from leakage, or more even. And that's a really big confound, because there's always going to be a high correlation.
Even at the longer time points?
Yeah. Well, yeah, obviously that gets less because the concentration in the blood gets lower. But nevertheless, even if it's only affecting the first third of your time series, it's still a major confound in terms of the leakage, because the leakage is largely encoded in that early part of the uptake curve anyway. And the point at which you see most evidence of that leakage is when you have the highest concentration in the blood pool, because that's what generates the difference that drives the diffusion of the gadolinium. And so that's the thing that worries me most about the concentration, the contrast agent-based methods, because you have this very strong correlation between the point spread function in the blood pool and the thing you're actually trying to measure, which is the leakage in the tissue.
Makes sense. That's helpful. On the diffusion-based method, it does seem a lot of the underlying assumptions of the model are related, to this kind of IVIM component for your assessment. I was a little surprised looking at the graphs that on the diffusivity measured using the relaxation corrected model, it seemed like the white matter was greater than the gray matter. You might have imagined if it's IVIM based, whether it's volume or flow related, it might actually show the opposite. Do you think, and more in general terms, do you think that IVIM like model has limitations in terms of this application, or in practice, does it seem to be good enough?
I think there are two questions there. One is, why are we seeing that diffusivity higher in white matter than grey matter? I think that was the point that you were making, was it? The blood pool. I completely agree. I think that seems wrong. Sorry, I've been. Can you hear me? Okay.
Yes.
Okay, it's mirror messages of mine. So that's an ongoing debate between myself and Lizzie, who's named on the screen at the moment. We're trying to get to the bottom of that. So yeah, to be determined. In terms of IVIM, I think something that I get to explore, but something that I think might be important is understanding the impact of exchange on IVIM. Because IVIM does assume that you've got two well-defined compartments with no exchange happening between them. It may be that on the timescales of the measurements used for IVIM exchanges are relevant, at least in the healthy brain. That may not be true in certain conditions. So I think there's work to be done there. But fundamentally, I don't think there's a problem with the idea of having a two-compartment model as long as you account for exchange between them when that's necessary.
Great. Thanks very much. Great.
Thank you very much. I think this is a good time to conclude this talk. Thank you very much, Geoff. We enjoyed quite a lot. We learned quite a lot. And see everyone next week.
Thanks very much, everyone. Bye.
Bye.
Thank you very much. That was great.